Siamo live, ok. Buonasera a tutti, ricominciamo gli incontri del JUG anche in presenza. Questa sera abbiamo un po' di gente in sala e ringraziamo 011 per averci ospitato anche quest'anno. Abbiamo Dimitri che ci presenta un talk dal titolo Legal JVM Dopes for Your Apps. Wow, so give steroids to the JVM without being outlawed. Ok. Niente, ricordatevi di iscrivervi al canale, di iscrivervi alla mailing list. Adesso stiamo cercando di mantenere un buon ritmo, dovremmo avere un talk il prossimo mese, anche magari uno subito inizio dicembre. E se avete delle idee scriveteci, noi siamo sempre pronti, aperti ad ospitare talk di qualsiasi livello. E buona serata e buon talk. Lascio la parola a 011 che ci dice qualcosa su di loro, visto che ci ospitano gentilmente. Grazie.
Grazie a tutti, grazie al JUG, siamo sempre entusiasti di ospitarvi perché siamo degli entusiasti di Java e quindi per noi è un onore ospitare JUG. 011 si occupa di sviluppo software in ambito e-commerce, in ambito AI, e utilizziamo molto questo linguaggio, quindi siamo sempre contenti di ospitarvi. Grazie a Dimitri, siamo veramente curiosi di scoprire queste DOPS per Java, per la JVM. Buon speech, a te la parola. Grazie.
So we can begin. Yes, we will talk about legal DOPS legal JVM DOPS for your apps. What does it mean? Is that in fact we include many useful pills right in the JDK, and it's easy to enable superpowers inside JVM that actually will change how your application behaves. And sometimes it can make your performance better, or sometimes it can save you money just by wasting your resources that you pay for. And this is a continuation for another talk, I'll mention it, where I discuss horizontal scaling. So here we kind of try to apply vertical scaling for our application, for some sample one, and see how the DOPS can change the behavior. And by the way, it's good to be here offline, so not too much of what I have here, but I have some stickers and some cable ties which you can easily grab. And if you have any questions, we're at the Java user group meeting. Just throw the questions, stop me, and we'll discuss it. I hope we're not too limited on time. Oh, that's great. So I do participate in OpenJDK development, which I love to do. Well, I wish to spend a bit more time on that. At the same time, I travel. It's my first time in Italy. I just arrived today. So, yeah, it's my pleasure to be here. Thank you so much for all that's what surrounds me. And the company not just participates in OpenJDK development, but releases its own distribution of OpenJDK called JDK, which is the recommended JDK for Spring Boot, and also one of well-known top OpenJDK distributions. We try to keep up with the releases timeline, and also not just the JDK, but we try to provide the entire stack, including Linux distribution, that empowers containers in particular, and it's called Alpaquita Linux. It is small and performant. And also a distribution of Graal VM Community Edition, which is called Liberica Native Image Kit, or NIC, how we call it. It's a nickname for the product. And we participate in different community activities around it. Is it an echo? Yes. Yeah, that's what I've recently mentioned. Now let's get back to what happens with our applications. I mentioned horizontal scaling, and there are certain problems related to it. And all that happens because we want to squeeze some effectiveness from our applications. But it rarely happens from the very beginning. We start by just developing our applications. So developers create code, and then developer and operations manage deployment of that code. And then there are some platform teams, maybe cloud ops, who manage big clusters where Java is not the only component running. And they probably don't really bother about JVM specifics, about any dopes. So we have to apply that, to be aware of that at this stage, or at the second stage, at least. So the source of the entire movement is, of course, cloud bills that business gets when our applications consume some actual physical resources. And as we deploy them in containers, that physical resources might be, well, over-provisioned. Because it's so convenient, just provide containers, and it's so convenient to consume containers for that cloud ops, just they run it. If it's stable, fine. Well, then business gets the check and says, well, it's probably too expensive. What is the actual resource utilization? 20%. What does it mean? So we could pay 5 times less. That's not always the case, because there are certain days where when we need more resources than usual, but we need to scale up and down, and here horizontal scaling helps us a lot, and we must plan it, but we also must plan some capacity that will help us survive while the actual horizontal scaling happens, because it's not instant. Yes, we know it's not always a great idea just to copy some recipe from the internet and apply it in your production. Let's try to test things, or just look at what we can study in our applications, what we can change, what we can observe by the changes. So it's a very kind of naive performance talk, which is measure different performance metrics, applying very easy applicable optimizations. So I love to talk about this application because at least I know how to run it. I wouldn't say I know how to write one, though I can read the code, but now you don't have to write code anymore, right? We are in the AI era. And I heard that the company that hosts us really prefers that. So yes, it's easy to write such an application using AI now. And I've tested very recent versions of everything, though not exactly. So I also started doing that in JDK 24 timeframe and slightly older Spring Boot timeframe, and the results were a bit different. I will mention that. Just sometimes the differences may be critical for you. All right. So we can optimize containers, we can optimize applications, but we have to optimize. Why? Because otherwise we will have to pay. So let's pay for developers' time, for performance engineers' time, but we'll save something from our resource usage. Well, we want to run some application effectively. And as I mentioned, I started with experiments in scaling it horizontally, trying to find optimal pod sizing. So imagine we have some limitation. It may be a big, bare metal server. And we can apply different pod sizing. And we will get very different performance results when we perform such construction of many pods or fewer pods of different size within the same hardware limitation. So the final results, for example, of how many requests per second we can survive is quite different. Sometimes it's like the application doesn't work because the pods are too small. And there was some optimal size found in such experiments. That's just a diagram for that, and we'll experiment with approximately the same kind of containers or pods. It doesn't matter in this talk. Either we run in Kubernetes or just using some simple container management system. We'll run our application in a clearly defined resource constraints, in particular memory and CPU. So networking is not that important in such a setup, because the database is in memory and we don't really depend on file I/O, etc. So we really depend on our CPU and memory resource. So we greatly depend on garbage collection. We'll see it in just a short time. But if we have many replicas of such application, we can reach like 20,000 requests per second for the entire big IO machine. But for a smaller pod, it's just a fraction of that value. And that fraction, and we'll study how we can improve applications behavior for that fraction of the entire deployment. We'll just stick to 500 requests per second. So we'll need 40 replicas of the application to reach the overall throughput. So first of all, we need to package it, right? We need to package our code. We need to create a container. That's probably my favorite slide ever, because here I can promote as much as possible. Is there any problem with the Docker file? Well, I would say, first of all, you don't need a Docker file at all. I'll just mention it later. But here are many different inefficiencies and even some potential dangers, like using the image called OpenJDK is dangerous. So you use the latest tag, and you also use an unsupported image here. So it's officially deprecated. This is an official image which is officially deprecated. So it's recommended right there on its page on Docker Hub to use another image. Just pick another image which is not deprecated. And also we use fedjar here, which is not the most effective way we can behave in a container. And, well, a very heavy scene here. We use default Java options. And no one will change it for us. So it will stay forever. So what are the pills that we applied, for example, in such Docker file? Just try to find one and name it. For example, here, is there any pill that we've provided to the JVM that will help our application to look stronger, to work better? This is the pill. It is memory, which is probably the most important one in our Java world. If we can help garbage collection, if we can help application to keep more data in memory, we're good. And if we just stick with default options, we won't provide that amount of memory to our application. It will be much, much smaller. And also, for example, we let it run with the default class loader. So it won't spend resources in unpacking jar files and using custom class loaders that will load classes from nested jar files. So it will help our application to start faster. And of course, we can optimize the runtime we are using here. We can use latest Java version. We can use optimized Liberica Lite and Alpaquita and whatever we prefer as our Java runtime. It can be J-linked, or it can be used as is. So there are already multiple dopes in such Docker file. We can simply give it our JVM. So they are not even sophisticated settings. We don't change the mode of operation. We just properly allocate resources. First of all, memory. And you can fix it later, by the way. So we can provide Java options later for the container, right? It just requires a restart. And the same kind of dope can be provided automatically. So here we had to perform some experiments, ensuring that, hey, this ratio of memory in container that would be given as the size of Java heap really works for us, really helps us. So we place this 80.0 right here. When we use buildpacks, which is a technology that allows to create containers from different kinds of applications just by invoking tools that bring other tools using containers that will assemble our application, that will deploy our application, not deploy, but will create the container that runs in different circumstances. And inside that container, there will be helpers that will calculate necessary or proposed heap size for us. So it will try to use as much memory as possible for the Java heap. And that usually helps our application. So we can simply invoke our build system command and get a container image made for us without writing a Docker file. And inside that container image, there will be a starter that calculates memory settings looking at the actual limits that we have in the container. So we can run it with different settings on different pod configurations and still get consistent results. Though we need to ensure that we rely on proper assumptions, so we can say, hey, let's save some headroom. We will use certain amount of native or carrier or platform threads, and each thread requires some native memory for its stack. So for example, if we use some application server that uses platform threads, like 250 threads, and each thread has a stack of 1 megabyte. We have longer stacks. What will it take for us? So it will require 250 megabytes of memory. So we have to reserve that memory. It's not a Java heap. It is a native memory. We have to reserve it, because otherwise our JVM won't run. So let's say we have 1 gigabyte of memory for our container. So we'll leave some headroom, right? Because we need to run the JVM itself. We need to allocate its memory for compilers, etc. So we'll need some headroom. We'll load some classes. Probably we know how many classes do we load. And that maps to some memory used to store that classes. And we'll say, hey, let's also subtract 250 megabytes, which will probably leave us, I don't know, 600, 700 megabytes for Java heap. So a script can do that for us. And if we run in a 2 gigabyte container, that script will provide us 1 gigabyte and 70 megabytes of memory for the Java heap, without any effort from developer side. Right? That's convenient. All right, let's study some aspects of the application's behavior. As I mentioned, we'll use only a fixed limited rate of requests to that application and look how it behaves. That's 500 requests per second. And we'll measure something that pretends to be latency. I will explain it later. We'll also see how the application starts before we put that load. I will try to do it more or less precisely using right measurement tools. So the application initial lifetime can be split into some juicy parts, just like above. We'll have three major parts. The startup part, when the application loads all the necessary classes, initializes everything. So it runs initializers, it runs all the starters, it starts beans, in case of some bean-based application. And that's the first phase. Next phase is, well, let's try to train the application. We start issuing requests, and first responses are very slow, and they require a lot of resources because we start executing in the interpreter, then fast compiler, then C2 compiler. So it takes resources, and our code becomes faster and faster, but the response times at this phase are not consistent. So we see pictures like in the right part of the slide. The values studied here, they can be considered as per second response times, average response times, from average response times and P99 response times in milliseconds. That's not an honest representation because sometimes it's less than 500 requests per second processed there. And the very initial numbers are much higher. They're like 700, 800, so an order of magnitude higher. Very bad response times for the very first responses. But if we average first multiple 100 ones, we'll get like 18 milliseconds, for example. So are there any questions regarding the plots? Because I will refer and present such plots all the way down the presentation. All right, so you see what happens. On the left plot, by the way, yeah, let's merge it back. We have two values. First is CPU consumed. So we have only 4 cores dedicated to such container. So the maximum amount of CPU we can consume is 400%. So it is the red line. And the blue line is memory in megabytes. The application starts and we eat memory more and more and more, and then we don't give it back because we have certain load and it's not turned off. If we would turn it off, probably the JVM would return some memory to the operating system. So it is also useful behavior, or if we lower the incoming rate, that also may be the case. It can help us to save the cost of the operating memory. So first of all, we consume a lot of memory. Can we consume less? How would we change anything to consume less memory? So this memory is mostly garbage. So what's the part of the JVM that managed the garbage for us? Yes, the garbage collector. So let's change it. And we know that it is a small pod. It's a small container. So let's change it to serial. We use the default G1 GC, and let's change it to serial GC. So what will happen? Well, here we can observe that using serial by default for smaller containers is a very right thing that JVM does. So it's not used by default for such containers, but it's still, in this example, it helps. So we observe both better latency, about the same CPU consumption, but much better memory consumption. So the footprint is much lower. You see, the scale on the left for memory is 800 megabytes. So we approach 800 megabytes, and the container is, what, 1 gigabyte, right? On the right, it's 400. So we can use 512 megabyte container. That's good. And we have even better latencies. Well, the qualitative picture looks about the same, but the actual values are slightly better. Well, that's not the only garbage collector we can use. Yes, and by the way, it's a nice thing, right? For small containers, JVM does that for us, but there's a job that says, let's use G1 everywhere by default. Let's make it fast, as fast as serial GC for small containers. Let's make it as less memory consuming as serial GC for small containers. As far as I know, we're not yet there, and you can see why. So low latency GCs. For this service, we try to stay within 100 milliseconds response times for the tail, right? For P99.9 of responses, measured by the workload generator. But with ZGC, we can try to squeeze much more from our application. Let's say we have new business requirements, and they say, please respond in 10 milliseconds. Is it possible with G1 GC? Probably not. So we can have 50, maybe 100, but not 10. Well, in such case, it also won't be 10, but that's because the load is a bit too high. But you see another result. I forgot that this container is actually not 1 gigabyte in memory. But how much?
10? 7.
8. So, and here we eat, if we summarize all the memory, so we don't measure heap here. We measure the footprint of the application, RSS. It is also not an honest metric. Sometimes it lies us a lot. Sometimes it can really lie a lot with ZGC, by the way, in all the Java versions, because it uses multi-mapping, and it just may report some very strange results. But it consumes the memory it is allowed to consume to provide you a very low latency. If we have that memory, why won't using it? Yeah, let's use it. And what do we see here? Well, we see much less spikes that are much lower. And if we look at the results, well, with serial, we have decreased the latency. We have decreased the footprint. We also have decreased the startup. And with any collector, we can use Spring AOT. We can explode the jar file into layered jar, or just a set of class files and libraries available to us. So I'll proceed with serial as the main garbage collector, which is combined with other JVM options, other dopings. And with ZGC, well, we use more memory. So we don't underutilize the resources of our container. We use that. And we improve some metrics. Like instead of getting 60 milliseconds for P99.9 of the response time, we get 19 milliseconds, which is great. So we started from 100 milliseconds. No work in the application, no work related to Kubernetes. Just a single JVM option, trivial one. Yeah, change your GC, but you have to understand what for, and you have to measure you can experiment, for example, with some canary deployment, right? So you may even forget about the actual load you're providing, right? If your canary deployment is live, it's fine. And you have metrics that are fine. Just look at the proper metrics your monitoring actually cares about. Sometimes you may say, well, we have said some artificial values, but your monitoring team will say, your production is ruined. Don't you see it? As I mentioned, G1 probably will become the default for all environments, which makes Java much more consistent. You don't have unpredictable results. You just have to think of some improvements, right? You may change it manually and you'll get benefits. Otherwise, you'll get the consistent behavior. You will always know that if there are default options, well, it will be G1 GC. It's much easier. And of course, ZGC is not the only low latency GC. We have two now, and both of them are now generational. In Java 25, we have generational Shenandoah, and that's also a low latency garbage collector. Well, there are interesting quirks, but we have it. And that's true for multiple versions. So even in version 17, I will explain later why is it important right now, but we have both those garbage collectors, non-generational, but that's still helpful. We can trade more memory for low latency. Of course, if you want to improve throughput, parallel GC will help us, right? Or G1 can be targeted to trade pause time for throughput. So we can achieve both goals. One of them, to have lower pauses or to have better throughput. We also can manage G1 footprint. So that goal of having single default garbage collector probably, is focused on those aspects of G1. And we've got better results with serial, but there are many more GC options we can apply. But nowadays, it's still much simpler than it used to be. Like tons of settings for G1, tons settings for CMS, right? Always copy it from internet to your production. And sometimes, well, we're running G1. Why do we still have all that CMS settings? Because it's legacy. I hope you don't get such questions anymore, right? So next brave idea, let's replace the JVM. We've got good results with serial GC. Why won't we go beyond that and use also only client compiler and an entire client VM? In fact, how many VMs do we have supplied in a full JDK distribution if it's kind of a default regular build? How many JVMs do we have? 3 to choose. It's server VM, client VM, and minimal VM. Minimal VM is kind of slow, so it's more for embedded, but client VM can be used in our cloud deployments or on-prem deployments. But in this example, you see we don't save any CPU after warm-up. And by the way, this part of warm-up, when we reach peak performance and we consume the time to performance, so in this plot, in this example, it only takes about 1-2 minutes, right? But how long does it take in real world? In your experience, have you measured it? Because if you construct such picture, you'll be very much surprised. Like this part may be tens of minutes, not tens of seconds. And we pay for resources that are consumed during that phase, because we need to keep it shorter. And those resources are usually higher than the resources spent for the same incoming rate during the rest of the application's lifetime, which may be infinite, which is much longer typically. Sometimes that's not true. But mostly the case is the application runs for a very long time compared to that initial phase. And we pay for resources to warm it up, because otherwise we won't be able to wait for it to start and respond as in a meaningful time. But we waste that resources. We don't use them afterwards. And we pay for them all the time. So here, we don't waste it with client VM. They are used. It's less effective. But also, you see, our response times got much worse. So we're not able to keep up with that 500 requests per second. And that's the problem. And the load generator still applies, it tries to apply the highest load it still can apply to that application. And we observe such bad response times. That's not always the case. If we have bigger headroom and we can still survive such incoming rate and we control that, we'll see a different result. So we'll see just slightly worse response times. But the warm-up time here, who can say how long is the warm-up on right plots? Well, we start getting consistent bad response times only after a few seconds, not after 1 minute. And this is true. So we warm up very quickly. Well, we still keep spending some CPU, but it's not that bad. So in fact, our warm-up time decreased significantly, even if we take into account this part. We still have improvements. So we decrease our warm-up time at least twice, but actually it may be decreased to just seconds instead of minutes. And we decrease our footprint, right? Because we use only client compiler, we use only serial GC. So now it is only 270 megabytes. Does it make sense for you? So instead of using huge container, we actually can stick to a slim one. And the static footprint is also lower. So it's like 26 megabytes for the JVM itself turns into 16. And we can still apply JLink and all the techniques we use to shrink our static footprint. And the actual RPS in this example decreased significantly. 2 times actually. Which may mean we just need 2 times more machines, but those machines are smaller. Like we don't need that much CPU in some circumstances. If we lower that incoming rate, if we say those pods will only receive 200 requests per second, that will also require less CPU, not just memory. So depending on the actual numbers, that can make sense for you. But if you don't measure, if you blindly apply this dope, it can blow up your production without any reason. Just it's some strange setting, dash client, and what happens? We don't keep up with the load anymore, or we just need too many pods. So take the hit or double the fleet. Well, some fancy technologies. As we have replaced C2 compiler with C1 compiler, or tiered combined C2 and C1 with C1, we can replace C2 compiler with a different one with Graal JIT. It works differently. It's written in Java, but it's been bootstrapped into a native library, so it can compile our code differently. JIT compile it differently. And you see, this is not exactly the same plot. Well, here, what we can observe? Longer warm-up, longer higher CPU usage, right? That's the specific of this compiler. We also have slightly different memory picture. Well, in the end, we have about the same memory usage. And the version of Graal JIT used here is the community version, based on what PetClinic provides us. So not a big difference. And if you look at the other pictures, we see the same longer warm-up, right? Though we don't warm up the compiler itself, we still have to do extra work sometimes. Does it work? Does it work? Well, probably not in this case. So we have much bigger base image because that JDK is not that optimized for cloud deployments. We have longer warm-up, and what's even worse, we have bad tail latencies for the steady state. Of course, the picture is different with Graal VM EE, right? It used to be included even in Oracle JDK, in JDK 24, but now in 25 it's no longer included. And that also means that probably there won't be up-to-date Java version support for Graal VM distributions. So for Java 26, you'll get new dopes from the JVM, right, from your JDK. But in Graal VM, you'll have a different story, concentrated around compiler and different languages support, but not keeping up with all the different JVM features you can imagine. Well, but we love Graal VM not for its dynamic compiler, but for, what would you say? For the native image, of course. So why would we apply Graal VM JIT? Let's apply a native image. Let's create a native image, and we can create a native image using buildpacks, or we can create a native image by hand, well, by providing some extra settings, of course. Anyway, we get the native binary, we placed it in a container. We provide the same memory settings. That's important, because by default, the JVM will use only 25% of your memory, available memory, and native image by default uses 80, which sometimes explains some of the results that we can observe. So here and there, we use same setting, same 20% for the heap. And you see, we don't have this part of our bool. Our startup is almost instant. It's not entirely instant, so we still have to run some initializers. We have to initialize bins, etc., but it's very, very short. So this is the leftover. And then there's a pause, and there's a pause as well. And we start our application, and we don't have that long warm-up phase because we don't have to perform JIT compilation, etc. We just have peak performance from the start. And that's the clear goal, and that's the clear win that we have here. And look at the memory. What we can see here. Well, basically, it's the same. So we have optimized the JVM previously by giving it some pills. And it already consumes about the same memory as native image. So by default, it runs, it builds with serial GC. In Liberica native image kit, you can use parallel GC with implemented it in Java. In Oracle Graal VM, for the native image, you can also use G1GC, which gives you many advantages, and it is kind of binary linked. It's the G1GC from OpenJDK. But here we compare serial to serial. Just say, let's consume as less memory as we can. It actually works fine. And we have good response times. Well, we don't have all that. Chop it away, throw it. Though you see some latencies are not that good, right? You can simply observe it by eye, by your eye, and your monitoring team can observe that. So you enable it in your canary deployment, and you see it if you have monitoring. If you don't have it, you'll be surprised. So the CPU consumption becomes consistent, right? It doesn't mean it becomes less. It's not true. The startup is not instant, but it's almost instant. And the warm-up phase, again, we can say it is 0, but it's not entirely true. We actually still perform some tasks. During first 20 seconds, we consume memory until we reach the GC steady state, right? So it depends on how do we look at our code. How do we look at our production? If we say, well, it responds, and the response time is consistent, it's 0. Well, the consumed heap changes, and it's not the same. Then the warm-up time is not 0, right? We still tune something inside the substrate VM to reach the steady state. So the footprint change, and as we have seen on those human-readable pictures, right? The actually measured latency is worse. And if we imagine P99.9 limit of 100 milliseconds, we're out of that limit. So we still can keep up with 500 requests per second, but we can't provide the desired latency. So if that's our SLA, it's broken. So we have either to optimize it, maybe experiment with parallel GC, etc. So we'll trade off something, maybe footprint, right, to get better latency. If it's not important to us, maybe that's our new SLA. Oh, well, we never needed 100. We always needed 151 until next release, where it turns into 200. Well, we see that it's nice to save memory. And that was a great work in OpenJDK aimed to help you to save memory. We waste a lot of memory. We need a lot of memory for Java objects just because Java is so object-oriented. We can perform synchronization on strings and do other nasty things. Well, all that information about objects is stored with every object in the object header. So we have to care about synchronization, hash codes, the class of the object. So for small objects, that's a big waste. Typically, we don't have memory consisting only of small objects, but the typical waste is around 10–20%, measured in the initial experiments for Project Lilliput. And Project Lilliput is about making those headers smaller. And it's called compact object headers. And in all those experiments, maybe we already had something being compact about objects. How do you think? So we had, look here, 400, 500 megabyte heaps, 7 gigabyte heaps. Those are compact heaps. Why? because they're all under 31 gigabyte. And with such small heaps, we can use compressed object pointers. So if we have fields in our objects that point to other objects, we don't have to put an entire address there, because our objects are aligned. So we can use compressed pointers, and those fields take less space. But what happens if, for example, we store a very large cache for our database in memory, in our heap? It is better to have larger cache, right? Because it saves our database round trips. We don't go to the database, we get the data from the cache, or put it to the cache. But we have to manage a big heap. And if the heap exceeds that 31 gigabyte boundary, approximately 31 gigabyte, slightly larger, but how much memory do we need to store the same number of objects? Let's see, 1 gazillion objects. Previously, 31 gigabyte was enough to store them. And if it's 1 gazillion and 1.2 gazillion objects, we'll need much more memory. So without compressed pointers, the leap in the heap size looks like we go from 31 gigabytes to 42, 47 gigabytes of memory. Like all that intermediate heap sizes are a dead zone. We can't store that many objects that are no longer referenced by compressed pointers. So in that case, saving on headers helps us a lot, because we save that additional 20% of memory, of heap memory. So we still can continue running with that heap sizes. And we can continue having lower poses. We can continue use a G1, GC. It makes a lot of sense. But does it make any sense for smaller applications? What do we measure? Do we measure heap, or do we measure the process footprint? The process footprint is much more important for us, because out-of-memory killer doesn't look at heap size, doesn't look at heap consumption. It actually looks at the process footprint. Well, if we compare our application behavior with compact object headers, we don't save anything in the process footprint. We even have worse CPU picture, right? The CPU usage doesn't drop after warm-up. So we still see the same, about like 60-ish second warm-up, right? So it decreases slightly, but it doesn't drop. It doesn't have that step. And we have about the same memory consumption. And again, our load rate was on the boundary where slightly worse response times turned into a disaster. So we are not able to keep with the incoming request rate. So we have much worse latencies. That's not always the case. And here I will show you different pictures. But you see the same thing happened, right? So P50 and P99 are much higher than they used to be. So we have about the same warm-up characteristics, but response time is worse. With older Spring that probably didn't have some bugs that affected performance, and it better kept up with the load, we actually could observe decrease in the process memory usage, which is nice, right, for our applications. So it gives us more confidence in our application stability. When the load comes, we have some extra headroom to survive. But only if we're able to keep up with the load, right? Otherwise, it blows up. So in this particular case, it wasn't as bad as what happened with the native image, for example, right? Or with client VM, especially. So that's still a significant drop. So we've enabled compact object headers with serial GC. That was a bit unexpected to me, but you must measure. I've seen such behavior in some benchmarks, micro benchmarks, but not those scenarios like here. And you see, if we are not able to keep up with the load, we see a very high response latency. So milliseconds turns to seconds. But it might be the reverse. If you measure in your environment, in your circumstances as requirements, you may observe even better latencies if you use some subcritical incoming request rates. Like here it was 4% improvement. Well, is it a great dope or not? Lilliput, what do you think?
What?
Yeah.
I'm a bit disappointed. Do you know why?
Well, it requires extra work. So I would expect such picture, but here it is a combination. So we have slightly worse response times, and we are not able to keep up with the incoming rate. But the load generator is not aware of it until it gets some responses. So it overloads it anyway, and only after that it backs off. So it becomes overloaded.
Yes, but why is it worse, the server-side performance? Why the JIT cannot have the after the warm-up going down and say, okay, I have generated better code and therefore the CPU runs.
Well, there is extra code to work with compact headers. So you have to decode, encode things, especially if you have some synchronization, you go to some tables. It costs you something. So it depends on the amount of GC work that you have, on the amount of synchronization that you have. So the amount of work with headers. It may be better. Again, it's the same implementation. So it didn't change much since Java 24. You can enable it if you still use JDK 24. You can enable preview features, enable compact object headers, use it. So I would say nothing critical was found. But yeah. But did you see those 31 gigabyte boundary applications? Some deployments floating on that boundary, trying to keep below the level. It's actually a popular case. I really meet that from time to time. So another big project that was integrated in OpenJDK even before Lilliput, but it was fixed along versions, and there were important fixes in JDK 24. And we have now kind of final or close to final version JDK 25. It's production ready, it's stable, it doesn't have any known big performance surprises. It is virtual threads. And with virtual threads, we can get back to the model when we process each request using a thread. It is almost always so. Again, I've heard about cases when it doesn't work good, but those are really extreme cases. So if you have extremely low latency and extremely high rate of incoming requests, well, it may happen. So in JDK 21, probably you started using that, right? Who already used virtual threads? Everyone. It's easy. Instead of creating new platform thread, just new thread. You say new virtual thread or new virtual thread pool, right? And it's all surrounded with all extra helpers that try to forget about all that complexities. It is also all compatible with structured concurrency APIs. It's easy. So no more max threads for your application service. This is true in JIT as well, right?
No.
It doesn't, no? So you still apply some max threads to virtual threads. Interesting.
We use a semaphore,
Semaphore.
but it's typically a bad idea because then you have an unlimited system.
Yes.
If you have a spike in the load, the system just creates like 3 times, 10 times the threads that was able to create before, and then the system just goes down. So we use the semaphore to kind of queue them up,
But
let the system trying to do the work.
is the boundary the same? Or is it
The
higher?
boundary is the same, yes. By
And-
default, yes. But
okay.
You can configure it.
Okay, so here I'm lying, it's about Tomcat. Just in JDK it's different. That's an important, it's good to know. In any case, it's important how virtual threads are managed, how mapping to platform threads is managed. And it is controlled by different settings. Like here it's max pool size in this case. Or just control your pools that use virtual threads. You still can, and probably should use some pooling by the reasons you've just heard. And virtual threads help to build that, to utilize that previously underutilized resources. So you can grab your unused CPU and use it for some computations because you can spawn many threads. No waiting for full synchronization. Just the overhead is anyway low, and you can use it. The logical model still has synchronization, still has logs. So if your algorithm blocks and all your threads wait for a single resource, you still will waste the CPU you have because those threads won't be on CPU, won't perform any useful work. Well, it's actually easy to enable virtual threads. And I think in all application servers, it will be easy eventually. Frameworks, application servers, because that's a very high-level setting. You just say, hey, please, you know what virtual threads are, use them where it's appropriate. And we can enable it. So in this case, we just enable virtual threads usage for incoming connections pool. And you see the warm-up period became much shorter. It's good, right? This phase, it's not intact because what would we do with the warm-up phase? Except threads provisioning, right? We can create them in advance if we have some min thread settings, and that will waste our memory, that will waste some time. Probably it can become shorter. Would we expect some memory savings? Actually, yes. Yes, because we don't waste native thread stacks. But we have on-heap thread stacks. Those are smaller, but we still use them. So the overall footprint is about the same. It's even higher, I think, right? So it was below 400, it's now slightly above 400. Not as expected. Though I really like that picture. And that is again a surprise. So we have less latency spikes for free. And it's hard to achieve that by regular means. What would you do with your application to avoid this? How would you profile that? It's not an easy task. You have to find the cause, if it's a GC, if it's something else, what happens? And here we've just enabled one setting. Probably that was related to some thread interaction. Great. Though you still see some suspicious P99 peaks. But after warm-up, the picture is great. So what we've achieved in the end, a simple setting. Let's turn it on. It works. Warm-up, actually faster. And latency, it's actually better. Again. And we can combine the settings with other achievements that we've got. Like here, again, we have serial garbage collector. We can also continue improving, for example, our startup phase. So we focused, or we got results for the steady state phase. Let's try to make our first phase better. Well, in Java 25, we have AUT cache. It's obsidious and some extras. So we now have a method profiling data stored in the AUT cache. We have linked classes in AUT cache, and it's easier to use. It doesn't reflect on performance, but it greatly reflects on the user experience. Have you tried using obsidious before? Since Java 8. Java 8. So if you use Java 8, well, you can use it. And it will help. So what do we struggle with? This part. But not only this, actually, if we talk about method profiles, we can dump our ahead of time cache information in different moments. What moments? For example, here, we've started our application. We say, hey, it is mostly initialized. We know the state. Let's dump it. Let's dump the info. But if we dump it here, we also have some method profiling information after the warm-up, after some real load. And we know that in later time, it doesn't change that much. So we can discover it, we can measure it, we can dump it right here. Or we can go simple way. Say, we know nothing, but we know that the application has started. It's good enough. We want just to lower the start time. So if we cache at start, you see the picture is a bit different. So we've narrowed this peak. Is it a good goal? Sometimes yes. If our application lifetime is comparable to that, or if the peak is quite wide, why not? And the rest of the picture stays the same, which is great. Because what happens with our code is about the same. Yes, we reuse the profile, which really impacts our compilation, JIT compilation, but the result looks very, very similar to the original one. What if we dump our data after warm-up? We would like to see much better warm-up curve, right? Because we know all the right compiler decisions. We don't have to recompile afterwards. Unfortunately, that doesn't really happen. So it helps us a little. but not that much as expected. So the pictures are quite similar. And what's even worse, we may see later latency spikes because we have some assumptions in our profile and they seem to be broken afterwards. So we have destabilized the stable execution phase. That's a danger of the pill. So be careful with steroids. Was a bit unexpected, though we can explain that, right? Sometimes that won't happen. You may be lucky, or you may get some benefits that are much better than any side effects you can observe. Why not? So you see, the metric that is being discussed a lot, startup, is not that important to me, but we can decrease it. And it's measurable. Yes, so there are many techniques. It's not as fast as native image when we started, but it's okay. 7 seconds for your startup, it's fine. What is not good here is that, yeah, we have greatly decreased latency, right? We tried to actually capture the moment that we warmed up, when we warmed up, and the expected result that the latency will be the same. Probably if we measure later, so we say, hey, it is also again a warm-up. It just requires less resources. So we can chop it in more phases. So this is the warm-up of warm-up, and then it will be a real steady state. And we must get the same number there. It depends on what do you want to get. Where do you want to stop? Beyond that, we have to store the data. We have to store the cache. So all that loaded classes, which we memory map on application startup, all that application profiles, it's not a big chunk of data, but still some data. We have to keep it in a file. And this file takes 127 megabytes. In this case, we put it into the container, right? Because we want to use it. So we ship our application with extra payload, static footprint. Well, now, after the Graal JIT has been extended from Oracle Java, what's the holy grail in OpenJDK? Project Leyden. That should help with startup without side effects of storing the state. Project Leyden is about stateless caching of useful data, not data beyond the data that's being kept now. First of all, it's caching of methods code, or storing ahead of time compiled code for some methods. So we don't have to start with a very slow version of a method, like interpreted or whatever. We start from some compiled version, machine code. So what's the expectation here? We still keep the same compatibility level. We don't have any effects of keeping a state because we don't store any heap data here, right? We only save something virtual machine related. And also some other data, dynamic proxies, whatever. And you can already try Project Leyden builds. You can build it yourself, or you can just take one of early access builds. Actually, one of two. What's the expectation? If we create the snapshot after the application is warmed up, what would you expect? What happens with your warm-up time?
Next run, smaller warm-up time.
Yeah, almost no warm-up time. That's the expectation. Even if we focus on the first phase, we still have the startup time. So it's not about zero startup time, it's still some startup time. It still consumed CPU, right? So it doesn't, it's not visibly lower. So here we consume like slightly above 3 cores, and on the right, when we create a dump, again, only conservatively after startup, we still consume over 3 cores at startup. About the same amount of memory and CPU during application's lifetime. And you see the CPU drops later. I'm going to share that results. The Leyden team, because I double checked it and it still looks valid. So we apply the same serial GC and we create AUT cache at startup, as I mentioned. You see, the picture is about the same, except the warm-up is longer, right? We have a higher response time for a longer time here. And the same is true for P99. What if we create what if we apply the Holy Grail scenario? The application had some training run with real training, with some real load, or we've deployed one instance as a pre-canary or whatever. I don't know what's the right term here for such a deployment, because we take an instance without cache, we train it, so it gets real load, we create the cache, I don't know, in production or in some staging system, and only after that we actually perform a release when container gets cache in it, the container image gets the cache in it, and all other replicas of that service start with that cache enabled, and they use that cache. So finally, do we have a shorter warm-up? It doesn't look so, right? About the same. The peaks look lower, and CPU spikes in the steady state, but I won't say it's a dramatic difference. And what's worse, we've got it again. We're not able to keep up with the incoming rate, which probably means, I'm not certain here, but it probably means we still continue running that AUT compiled versions of methods. And their machine code is not as effective as what JIT produces. So our decision is to keep this version, and it is worse than the version that we've had in the normal run. And we're not able to keep up with the load. Sad. So yes, we have increased latency, etc. But again, if we can split our pods, if we use more but smaller pods, if we can lower requirements, we say, okay, we will survive only 400 requests per second. I don't see the number here. I should check. What was the actual number? Probably it wasn't too low. It was also 200 and something, or 400 and something requests per second maximum. So if we create that cache at startup, it is also about that 120 megabytes. In JDK 25, if you remember, it's 127 megabytes. So here it is more effective probably, right? But about the same size. If we add methods, machine code for methods, we have 143 megabytes. It's a conservatively compiled code, so it will probably run on different machines, but it is slower. And we wasted like 23 megabytes, and it's not able to keep up with the load. So what's good? we can always be smart guys, just measure everything, realize what are our actual requirements, what can we change, what we can break, and find the right pod sizing, find the right tunings, find the right dopes for our JVM. Just remember of the resources that we use. We are limited on that. And yeah, and those examples, only two resources were in the focus, CPU and memory. And actually, that's what, and also static footprint, right? Disk size. That's also a current focus of the JVM work. I mentioned headrooms many times. And by the way, here ZGC is mentioned, and we can say, hey, ZGC, please use less memory. Don't do that. Don't consume 7 gigabytes of heap. Just try to consume less, and it will. It will try. It's the only garbage collector that's able to do it. Probably one of 2 meaningful tunings in ZGC left. That's wonderful. You don't have to remember many JVM options for your garbage collector. Just remember 2 of them. And by the way, if we have ZGC, and this is Project Leyden, and we have that awful situation, and we have bad latencies, what would be an easy solution here? So this is serial GC, and it's blown. And we've previously seen that using ZGC can lower our latency.
Yeah, but if the problem is that the generated quality of the machine code is bad,
yes,
the GC
yes, probably that won't help. And that was the prepared joke. This ZGC is not yet supported in Project Leyden. So with AOT cache, but you can try Shenandoah. In fact, it is funny, but yeah, the current state of things is it's a work in progress. So nice. We have all that pre-release versions of JDK, JDK 25, ZGC generational, Shenandoah generational. We also have things that I didn't mention, like string deduplication. It doesn't help on such heaps, but you still can use it. Compact strings since Java 9. We don't have them in Java 8. So in fact, many deployments still run on all the JDKs. It's not that bad. We have some dopes in all the JDKs. I mentioned we have AppCDS even in JDK 8, and for 21, that gives some meaningful results, right? So we can we can improve CPU usage here. We can improve startup time here. Project CRaC, which we can use in JDK 21. So we don't have yet builds with CRaC for 25. Probably we will have once. It's not a commitment, but an expectation from our company. We can cut this plot at the necessary point, in theory. In practice, we only can cut it here after startup because of all the connections that application has. And cutting means, at this point, we say, hey, JVM, save your entire state on disk in a file, in a set of files. And it will do it. And next time, and we can put that state in a container image and restore from that state on next runs. The state is much higher. The static footprint is much higher. And the result is not stateless. So we save entire state, including heap, which means for certain things, like, for example, secure random, we need special handlers to patch the image when we restore it, to have different values. And not just for that purpose, so different libraries require patching for CRaC, but sometimes it really may be useful, and it is compatible with JDK 21. But what happens with older JDKs? Yeah, for 17, we still can use AppCDS and CRaC, but what happens for even older ones? We have that applications up and running without developer teams working on them. Probably they still run on an LTS version of JDK, so they get security updates, but not performance improvements mostly for all that long supported versions. Here where Fuse JDK idea comes to the scene. We can take a newer JVM and put it inside an older JDK. So we can make a combination which allows to continue running older applications, but use all new, not all, but many new JVM features. Migrate to newer JVM flags that only requires your platform team's efforts. It doesn't require any developer efforts. And we can start observing benefits from those new JVM features. Less memory consumption, better throughput. To me, the most important one is ability to work with huge heaps. So we can scale our applications finally. If they run on JDK 8, and we have very bad latencies, we can't use larger instances. Sometimes it's not really, it doesn't make sense to scale them horizontally. We still have bad latencies, etc. And we can finally scale them vertically. We can apply newer versions of AppCDS. We can apply GC settings such as ZGC, non-generational, but still. And some other aspects like new intrinsics for the JIT compiler, improvements in G1, improvements in zlib compression. They all freely help applications without changing the code. Dopes. It can be measured, and those really help. Of course, all the numbers are tricky, but in fact, you simply take your application, change the JDK, and you get optimizations from newer versions. You can better latency, you can better throughput. Sometimes you may see some regressions, of course, because there are trade-offs. Your workload may depend on certain behavior specifics on a particular version of your JDK. But what's important, there are all the frameworks, and we know specific cases where some older frameworks like Spring 2 can be combined with such Fuse JDKs. So in our case, it's called Liberica JDK Performance Edition. So it's still LTS, can be applied to that legacy, still supported versions of Spring Boot. Gives great results. After that, path forward. We have time to actually migrate our applications. If they work better, if they consume less resources, or if they can utilize existing resources for better SLAs, developers actually have some time to rewrite the code to the new version of Java. I hope that's the goal. Just don't stay on that old versions. Migrate to new ones. Or, well, bury the application. We know such cases. Recently on DevX Belgium, some guys approached and told me the story like, we know the service suffers, but it will be just shut down in 2 years. and we keep it running for 2 years, we suffer, but we know the date when it will be over. Right. Some materials probably already visited our blog or the YouTube channel that we have. It's called CyberJar. If not, I recommend doing that. Okay, do we have any more questions?
Yeah.
You mentioned the scripts to auto-tune JVM parameters without using Dockerfile or buildpacks.
Yes.
If your CI pipeline or something forces you to use Docker files for whatever reason, you can change that. Can you put those scripts or optimized scripts in a Docker file without using buildpacks?
Yes. Technically, you can. It's a Go program. It reads several environment variables, and that's it. So it's not too complicated. I've never done that, but I know technically possible. I'm thinking of making an example of like inventing your own build pack, inventing a wheel. Because if you need a Docker file, though you'll have to manage how new versions of the script comes to you, right, etc. So yeah, it's possible. And of course, it's not an ideal tool. So it may fail. It may calculate the value improperly. It typically is solved using the right headroom number, but yeah.
Are you aware of work being done on the IoT and compact object headers to improve them, because they were supposed to work better, but they seem not to? So,
Well, it's not yet a default. So maybe in this release and upcoming releases, things may be improved. At the same time, the plan was to go further and have Lilliput 2, which is a different implementation, and it probably has even higher overheads.
yeah, well, for sure.
So measure, yeah. I'm not sure what will happen next. At least there was a plan to make Lilliput 1 default. So beware. With every new Java version, you have to compare your performance. What has changed? What default has changed? And of course, all the degradation examples they're not so typical. So it's much more frequent to see such applications underloaded because they depend on the database, on other services if you have some microservice architecture, and they likely won't suffer that much. So if they're CPU intensive or GC pressure intensive, then yes. So what do you think? Does it make any sense to apply any of those dopes? Which one is the safest and the best?
I think from all this presentation here, the one that comes out best is virtual threads. Actually.
Virtual threads, yeah, surprisingly, and also serial GC, I would say,
yes.
for smaller containers. But it's enabled automatically. That's a wise default that we have. The default which works against us is the ratio of memory used for your Java heap. Just remember, it is very suboptimal, but it's at the same time it's very conservative, so it saves you from errors.
Yeah. I think I read by default is 25%.
25%, yeah.
So you were suggesting, like you presented a slide with 80%.
Yes.
So yeah, it's a big difference.
Yeah, but it can be simply changed because there are applications that mostly consume direct memory buffers. It's a new legacy in the cloud. Yeah. All right. So maybe there are some people online who have questions.
No, we don't have questions from the chat, so I think we can wrap it up. So thank you very much for this presentation.
Thanks for surviving 1 hour and 40 minutes. Yes. Yeah. 1:32.